It's a long question, and we're going to go step by step. It's a long question. So here's the function, f of t, which is t cubed minus 12t squared plus 36t. A particle moves according to a law of motion, and this is the law of motion, where t is greater than or equal to 0 and is measured in seconds, and f of t is distance and is measured in feet. Okay, so here's our first question, part A. Find the velocity at time t. Velocity at time t. What do I have to do? Do these bother you?
You have to differentiate.
Yes, please start differentiating. I just need to draw my notes. So v of t is f prime of t, sorry about that, which is 3t squared minus 24t plus 36. So far, so good? Perfect. What is the velocity after 3 seconds? Part B. How do I determine the velocity after 3 seconds?
3 into t.
So it's 3 times 9 minus 24 times 3 and plus 36. If you give me this number, so 27 minus 24 times 3 and plus 36, I got minus 9. Correct me if I'm wrong, please. Is it 27, 24 times 3 plus 36? I got minus 9. Measurement unit.
Feet per second.
Very good. Okay, so careful with this negative 9 feet per second. I cannot drive at negative 5 feet. It only says that the particle moves to the right, it has a positive direction of the velocity. If it moves to the left, it has a negative direction of the velocity. That's all it means. Also, if I throw up in the air, a ball up in the air, then the velocity is positive, and when it comes back, the velocity is negative. It doesn't mean that it only means direction, positive, negative direction. That's all it means. Okay, part C. In part C, they want, when is the particle at rest? When is the particle at rest? When is your car at rest?
Vt is equal to 0.
Excellent. When v of t is 0, which means 3t squared minus 24t plus 36 equals 0. What do we do? Next.
Add the 30, we'll subtract the 36 over here. Oh, wait, no. We did what, 3 first?
We will divide both sides by 3 to clean it up. Please clean it up. So we have t squared minus 8t plus 12 equals 0. And obviously, I'm hoping for a quick resolution here. Do I have a quick solution? If not, I'll use the quadratic formula. Yes, please.
It's t minus 2, t minus 6.
Perfect. So we have t equals 2 seconds and t equals 6 seconds. So I don't know what this particle is doing, but I know for sure that it starts moving right now. 2 seconds later, the velocity is 0. And also, from the starting point, 6 seconds later, the velocity is 0. Part D. When is the particle moving in the positive direction? So we're going to do this. We are told that time is greater than or equal to 0. Yes, it cannot be infinity, but you know what I mean. I am going to put the 2 and 6 in there because I know the velocity is 0 at those points. Here is the velocity function. Okay. If I want to rewrite it, I like products. Products are much easier to work with. So the product was basically 3, t minus 2, t minus 6. So look at this product and please plug in 1 or plug in 0 if you want, it doesn't matter. If you plug in 0, you know it's positive, right? It's 36. Or plug in 1, negative, negative, positive, positive. Plug in 3 and give me the sign. I don't care for the number. I just want you to plug in a number and get in between 2 and 6 and give me the answer, the sign of the answer. Please plug in 3 here. So yes, because 3 minus 2 is positive and 3 minus 6 is negative, of course. And plug in 10. So where is the particle moving, according to the question, in the positive direction?
Between 2 and 6. Oh wait, visiting 0 and 2, 6 and 8.
Exactly. So positive direction. For t in the interval 0 to union 6 infinity. 0 to union 6 infinity. Find the total distance traveled during the first 8 seconds. E. Total distance between 0 and 8. So total distance will be the absolute value between s of 2 and s of 0. S stands for distance, but I have to use f because that's what we have. F of 2 minus f of 0 plus f of 6 minus f of 2 in absolute value plus the absolute value of f of 8 minus f of 6. Let's explain this and talk about it before we continue. So it appears that this particle moves in the positive direction for the first 2 seconds, between 0 and 2. For the next 4 seconds, it moves in the negative direction. And then for 2 more seconds, it moves in the positive direction. I have to add all these distances. So it moves in the positive direction between, so s of 2 minus s of 0. Then it moves in the negative direction, but still I have to add the distance. I don't care which direction it's going, it's still accumulating distance. Is that clear? So it goes from right to left, from left to right, 2 seconds, and then back 4 seconds, and then back 2 seconds. So that's why s of 2 minus s of 0 would be a distance. S of 6 minus s of 2 would be a different distance in absolute value, because it has to be positive. And then s of 8 minus s of 6, or f of 8 minus f of 6. So let's put the function in the graphing calculator. Here it is. In y equals, we have x cubed, and we have minus 12 x squared, and plus 36 x. And then go to second and table. I have to do table set. Sorry about that, because it goes back in my case, back to default. Okay, so I need 0, I need 2, I need 6, I need 8. So I would have First absolute value, 32 minus 0. Second absolute value, 0 minus 32. Third absolute value, 32 minus 0. Any questions on this so far? Any questions? Okay, so then I will write the absolute value of 32 minus 0 plus the absolute value of 0 minus 32 plus the absolute value of 32 minus 0. Obviously, 32 plus 32 plus 32 is 96. Measurement unit.
Feet.
Yes, of course. Thank you very much. Okay, this was E. F. Draw a diagram to illustrate the motion of the particle. I already showed it with my hands. Here it is. At time t equals 0, the particle moves in the positive direction for 2 seconds. Then for 4 seconds, goes this way. And this is time t equals 6. And then it goes back 2 seconds for time t equals 8. So in this is the direction. So it goes to the right 2 seconds, to the left 4 seconds, and then to the right 2 seconds. So basically, in 8 seconds is exactly where it started. At the same position where it started. Okay, part G. Find the acceleration at time t and after 3 seconds. The acceleration function is the first, sorry.
V prime T and F double prime T.
Excellent. Okay, so we go back to V. Here's V. So 6t minus 24. We're also asked to find the velocity at 3. Fine. I meant A of 3. So 6 times 3 minus 24. And how much is that? (18 minus 24).
-6.
-6. Measurement unit, please. Let's think. It's the rate of change of velocity with respect to time. The measurement unit for velocity over the measurement unit for time. Exactly. Feet per second squared.
Oh, okay.
Right? Feet per second over second. Feet per second squared. Okay. When is the particle speeding up and when it is slowing down? And that's finally Colby's question. So please pay attention to this table. I want V of t first, and I want A of t. It doesn't really matter. If you put A first and V second, it doesn't matter. Can you please tell me where is A of t 0? At 4 indeed. 0, 2, 4, 6, 8. We already know from the first part or the second part that the velocity is 0 at 2 and 6. Now we know that the acceleration is 0 at 4. We already studied the sign of the velocity a few minutes ago, and we know that the particle is moving in the positive direction, negative direction, positive direction. Now I would like to study the sign of the acceleration. The acceleration function is 6t minus 24. Plug a number in before 4 and tell me the sign, just the sign. Negative. And after 0? We knew that because it's a linear function with a positive slope, so it has to be negative and then positive. No worries there. You don't have to plug in anything. Obviously, we see here we have several subintervals. We have a subinterval between 0 and 2, another subinterval between 2 and 4, another one between 4 and 6, and another one between 6 and 8. Agreed? Okay, now, let's see what happens on the first subinterval. On the first subinterval, the velocity is going in the positive direction, but the acceleration is against this force. They're not helping one another. Like I ride my bike and there is a back wind. No, I ride my bike and there is a front wind. So the velocity is going this way, but the acceleration is pushing the particle back. So what do you think is the particle doing? Speeding up or slowing down? Okay. In the second subinterval between 2 and 4, the velocity is going this way, but so is the acceleration. So what happens now between 2 and 4? They are helping one another. Speeding up. On the next subinterval, between 4 and 6, the velocity is going this way, but the acceleration, the velocity is going this way, but the acceleration is going this way.
Slowing down.
Slowing down. On the last subinterval, both of them are in the positive direction. They're helping one another. Speeding up. Is this clear now?
Weather sign gave you the same exact equation.
Oh, okay.
So I had those intervals that you have down there for slowing up and speeding up and slowing down. I had, but I think I must have just put like a bracket where it shouldn't have been or something, because it gave me the wrong answer. Now on the speeding up part, I got that one right. The slowing down part, they said I got it wrong. So I think I just did.
That's okay. But is it clear
Yes.
how we think about it?
Yes.
Excellent. Everyone else, any questions? Okay, perfect. So now, just for a minute, I'd like to go back. So we looked at the motion problems. Did we look at the tank, volume of the tank of water? No, so we want to look at that. But I also would like to quickly explain something about the marginal cost function. Is that okay? Okay. This is in anticipation of section 3.10, where we really look at this again. But I think it's important to talk about it right now. Okay, so here's a function, f of x. Of course, there is a point P, yes, our best friend, and there is a point, his best friend, Q. And of course, this has x, and of course, what is the y coordinate? Right. And of course, this time, you're going to say, yes, it's x plus h, because we've done this several times. Well, this time I'm going to change the notation. I'm going to say dx, which is h, lowercase h, right? A little bit of x, right? So obviously, this is the dx. And also, the same thing, the same distance can be denoted by delta x. Why do we need two notations? In a minute, I'll explain. So this must be x plus delta x or x plus dx. Dx and delta x are identical. So then, can anyone give us the y coordinate of q? And please use x plus dx. F of x plus dx. Of course, it's the same with f of x plus delta x. Okay. So dx is called the differential of x. In plain English, a minor change in x, a minor error in x. delta x is the change in x. They are the same. Okay. So we have a function. This is our function, whatever you wanted it to be. Let's say it's the area of a disk. But we have a minor error in the radius. So the radius is not always 10 centimeters. It could be 10 centimeters plus a little bit or minus a little bit. So remember, we are zooming in. Q and P are very close to each other, but I have to zoom in to explain what I'm doing. So there is a dx or delta x, a minor error in the radius of the disk, and this is the area of the disk. Okay, so obviously a minor error of dx or delta x creates an error in the function. What is the exact error in the function? So change in x, exact change in x. What is what it's called delta y, which is the exact change in the function triggered by delta x, which is the same with the dx. Can anyone point out or say, yes, if there is a minor error in x, that triggers this exact change in the function dy, in the function y? Can anyone dictate that exact change? Look at the graph and say the exact change is, and I will write it down if it's correct. Colby, save me. No one wants to talk to me today.
I mean, I see like where it would be on the graph. I just,
Exactly, just read it, of course. I want you to read it.
well, delta y would be the gap in between.
Of course, f of x plus delta x minus f of x. Same with f of x plus dx minus f of x, of course. So if I move p to q, I create this gap. And this gap is created by this gap. It's very clear, right? So this gap in x creates this gap in y. Agreed? Good. So that's the exact change in the function f of x triggered by a minor change in x. Right? Okay, so this piece then on the graph is delta y. The exact change in y. Okay, bear with me one more second. Of course, I am going to draw what? At P. Like we always did, the tangent line at P. I'm going to extend it. I'm going to extend the vertical line going through Q. And of course I created, what did I create? A right triangle in D. So one more time, what did I do? I drew the tangent at P. I extended it so it crossed the vertical line through Q. Okay. I'm going to remove the pink triangle, put it on the side because I want to show something. And I don't want to put more stuff on that, in that graph. So this is P. How much is this?
It's dx.
Excellent. Stay with me. I have no idea what this is. Not yet, anyway. And I'm going to ask you, what is the slope of this line? 10p. I want to determine the slope of the tangent line at P. Can anyone give us the slope of the tangent line going through P?
Question mark over dx.
Say it again.
Question mark over dx.
You're way ahead of me, which I love it. I do love it. Okay, so can anyone tell us what is the slope of the tangent line? What does it equal to? The slope of the tangent line at P. Give it a shot.
I was gonna say it would be the
Yes,
derivative of
at x. Of course. Of course. That's what it is. Yes. F prime of x. Indeed. The x coordinate of P is x. The slope of the tangent line at P must be f prime of x. No question. Excellent. Okay, now, forget about this. And I hope you agree that the slope of the tangent at P is also rise over run, which is the question mark divided by dx. And now I know that this must be equal to f prime of x. And now I want you to tell me what could this be.
dy.
That's why I said you were a month ahead of me. Indeed, this must be dy. See, I wasn't 100% honest with you. We couldn't discuss this earlier. Indeed, f prime can be denoted or replaced by the notation dy over dx. However, dx has a meaning by itself, and dy has a meaning by itself. I couldn't tell you that earlier. So this notation makes this, but also this piece has a meaning by itself, and this dx has a meaning by itself. Okay, what are they? And I'll go back to the graph. So dx is the differential. We wrote that again, before. Differential of x. And of course dy is differential of y. Can anyone solve this equation for dy? Here, I helped you. Say it again? Yes, but I want you to solve this equation for dy.
You mean just like rearrange it?
It's a proportion. That's why I put over 1, so you can cross multiply and give me dy.
Well, I guess I don't have the numbers again. Dy is equal to f prime of x times dx.
That's it. That's all I want you to say. That's all I need. This is carving stone. It's a very important concept. The differential of y does not equal the derivative of y. Okay, so the derivative of y or f prime is one thing. The differential of y is the derivative times dx. So when we're asked to find f prime, then we are asked to find dy over dx. But when we are asked to find dy, we will write f prime of x dx. Do not confuse these two. They're not the same. The first one is a derivative function. The second one is the differential of y. The differential of y is, and now we can go back to our graph. So this is the derivative, and this is the differential of y. What is this? The approximate change in y triggered by, I'm going to put it in right in a minute. This represents the approximate, the estimate change, the estimated change of y of the function triggered by a minor change in x. Okay, let's take a look. This is what again? dy. And you can say, wait a minute, you're telling me that these are close? Very close. Because Q is not here. Q is here. Therefore, the exact change can be approximated by the estimated change. So delta y is approximately dy. Again, this is the estimate of the change using f prime. This does not use f prime. This is the exact change in y. The other one is an estimate. And since we're here now, we're talking about that, let's finish it up. Can anyone give us again the definition of delta y? Because I would like to replace it. What does delta y equal to? Delta, this delta is the uppercase delta. The other delta from the delta epsilon definition is this lowercase delta, right? So this is the lowercase, this is the uppercase delta. It's still delta. So can anyone tell us again what is the exact change?
F of x plus capital delta x.
Yes. I'm going to write the x this time. You're going to see why. Minus f of x, indeed, approximately. And we know dy is not a derivative, but yes, the differential of y, which is f prime of x dx. Okay. Notice that I put the approximate. They are not equal. The exact change does not equal the estimate. Okay, so all I would like to do now is just move f of x to the other side. So I have f of x plus dx is approximately f of x plus f prime of x dx. This is a major result. As big as the definition of the derivative using the limit, as big as the continuity at the point, big, big, big important result. And since we're talking about it, I would like to look at a problem. Do you have any questions so far? Any questions? Any questions? Okay, so let's take a look at this, because I would like us to apply it. Apply the result in any of these problems. It doesn't matter. Okay, here's one situation, and we can switch to something else, but this caught my eye. The radius of the circle of this, because I mentioned that a few minutes ago, is given as 24 centimeters with a maximum error in measurement of 0.2. Who did that? Who did that? Which page was it on now? Here. Please stay. It's not going to. Never mind. Okay. Use differentials. Use differentials to estimate. We're not asked to find delta y, but we're asked to find dy. Correct. Right? So we're asked to find the differential, not the derivative, right? The maximum error. So use differentials to estimate not delta y, but dy, to estimate the maximum error in the calculated area of the disk, and then the relative error, percentage error, that can wait. So can anyone tell us what does 24 represent? Look at the graph from our function from the very beginning. What does 24 represent? X. We're talking about x. We're talking about, so this is the area. We haven't gotten to the function yet. So the radius of a circular disk is given to be, or as 24 centimeters. With the maximum error in measurement of 0.2. What does 0.2 represent?
Dx.
Of course, it's dx. Use differentials to estimate the maximum error in the calculated area of the disk. That's the function. So let's copy the information we have. So what we have so far. What we have so far. So this is problem 34 on page 255. We have x, which is 24 centimeters. We have dx, which is 0.2 centimeters. And we are asked to find the estimated error in the area. So what do I have to determine? How do I write it? Do I write delta A or do I write dA? Am I asked to find the exact change triggered by 0.2? Or am I asked to find the estimate triggered by 0.2? Good. So then I'm asked to find dA, not delta A. So the function, which here is plain y, in our case is the area of the disk. So I'm not asked to find the exact change, although I could. How do I determine? In case I'm asked to find the exact change, how will I determine the exact change? The area of minus the area of. The area of,
24.
exactly, and minus the area of, exactly. That will be the exact. But this is not what we are asked to determine. We're asked to determine or estimate the error. What will that be?
That's the derivative of
24 multiplied by,
0.2.
that's it. That's it. I don't have the function yet. I can determine a prime of 24 before I find the function, but that's exactly what I need. I'm not asked to determine the exact change triggered by 0.2, which will trigger some error in the area of the disk, because the radius is not 24. Is 24 plus 0.2 or maybe 24 minus 0.2? I don't know. It doesn't matter, really. It could be plus or minus 0.2. But this would be the exact change. I don't want that. I want to determine, we can determine both, obviously. But I want to determine the estimate. Okay, so now let's continue with the area of the disk. So how do I determine the area of a disk? Yes. In this case, because we denoted the radius by x, I'm going to stick with x. Good. So now I'm ready to find dA. Not plugging in anything yet because I want to find a dA first. So what does dA equal to? 2 pi x multiplied by, look at the formula. It's in your notes. The formula for dA or dy is f prime of x times dx, indeed. Good. So then dA, the estimated error, will be 2 times pi times 24 times 0.2. That's it. So approximately 2 times pi times 24 times 0.2, and I got approximately 30.16. I'm waiting for the measurement unit.
centimeters squared.
Excellent. Excellent. Okay. Let's look at a volume situation of the volume of water in a tank, and then we can start 3.9. At least one more application. Any questions on the previous one? We did not determine the relative error, or we can do that later in 3.10. I just want you to see an application of the approximate or the estimate. So the exact change is determined with the function. The estimated change triggered by dx is determined with dy, a prime in this case of x dx or f prime of x dx. Okay. If a tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes, then Torricelli's law gives a volume V of water remaining in the tank after t minutes. So this is basically V of t. I don't like the fact that they don't write V of t in there. I'm going to write V of t. Find the rate at which water is draining from the tank after blah, blah, blah minutes. At what time is the water flowing out the fastest and the slowest, and summarize your findings. So we're asked to determine the rate of change of volume with respect to time. What does that mean? What do I have to do?
Just really wants the derivative.
Of course, absolutely. Thank you. Okay, so we're looking at problem 18 on page 234. And we have V of t, 5,000, 1 minus 1 over 40t, everything squared, for t between 0 and 40. So they want the rate of change after 0, 5, 10, 20, and 40 minutes. We have to determine the derivative. What is the derivative of this function? We bring down the power, 10,000, times 2 minus 1, multiplied by the inner function prime.
That's just going to be. It gets rid of the 1, so it's just negative. Yeah.
Very good. 1 prime is 0, but negative 1 over 40 times t is negative 1 over 40. Okay. I will simplify. So 1,000 divided by 4, negative 250, because I simplify 1, 0. And then I have 1 minus 1 over 40t, and I want to present it in correct order. 25 over 4t minus 250. I distributed. Negative 250 to negative 1 over 40, and I simplified it 0. It's positive now, 25 over 4, and then I distributed negative 250 to 1, and I get that. Next step, I have a simplified form of V prime. I'm going to put in the calculator and then plug in what?
5, 10, 20.
Good. Ready? So 25 over 4t minus 250 in the calculator in y equals? Delete if you have anything in there. So 25 over 4 in parentheses, please. 25 over 4. If you have better options, don't put parentheses. But if you don't have better options, please put parentheses. So 25 over 4 in parentheses times x minus 250. And then with second and table, I plug in 0 and 5 and 10 and 20 and finally 40. And I copy. Why is the rate of change negative? Because the volume is decreasing. Very good. So negative 250, negative 218.8, negative 187.5, negative 125 and 0. I need the measurement unit. What is the measurement unit of all these numbers? It's a rate of change. The measurement unit for the top over the measurement unit for the denominator. Say it again.
Something over minutes on what is measured in.
Okay,
What was it, gallons?
thank you. So that's the measurement unit for the rate of change of volume with respect to time, gallons per minute. Excellent. So now the question is finally asking us, when is the water flowing out the fastest?
At 0.
When it's full, right? When we open at 0. So obviously 250 is the fastest. When is the slowest?
40.
When there is nothing left in the tank. That's the slowest rate of change. So 3.7 were simply applications of differentiation rules in different models, in that different situations that model real life occurrences, like the volume of water in a tank, if we try to drain it, the motion of the particle moving from left to right or right to left. What else we looked at? Marginal cost, all sorts of applications with differentiation. Questions? Questions?